So good morning still. Today in this platform session, we are 6 presentations. Each will be 10 minutes presentation, 5 minutes questions. We'll try to stick to that. We are here during the session and helping to coordinate. My name is Piotr Zaborowski from Open Geospatial Consortium, as we are involved in these activities from not provider side, just simply to look what are the trends. And here is the Wagner.
Yeah, good morning. My name is Wolfgang Wagner from the Technical University in Vienna.
And welcome the first speaker, Gilberto Camara. Will talk about the recent outcomes from his experiments and projects. Welcome.
Well, thank you very, very much, and thanks for the organizers. And while we're at it, my talk is about interoperability and reproducibility, but I couldn't resist this beautiful city in Vienna and showing one picture, which is in the Kunsthistorisches Museum of my favorite painter, Peter Bruegel. You should see the Bruegels at the Kunsthistorisches. And this is the Tower of Babel, for reasons that will be apparent shortly. The trenches I'm in are both. Basically, I've been a developer of a big Earth observation data analytics, a package called SITS, which is an end-to-end software for Earth observation data analysis, which does everything that you want to do with time series of Sentinels and Landsat. But I'm also from other side of the trenches for the 85% of people who live in the Global South. And as far as I can see, I'm the only guy from the Global South here. Now, the Greeks knew that no one loves the messenger who brings bad news. Sorry. But the message I came to you is simple. Interoperability in big observation data, there was a discussion between Peter and Anna before lunch, is unlikely to happen. Get over it. And the other messages, there's a good side to this. Now, why is it unlikely to happen? Well, the examples, successful examples of interoperability we've ever found in computer science, in IT, first there is theory, sound theory. And then the interoperability develops from the sound theory. Key example, relational model. Without relational model, there will be no billion-dollar industry of relational database management systems. Second example, closer to home, the 9-intersection dimension extended model by my good friend Max Ziegenhofer and Clementini. Without that model, there will be no OGC simple features. So theory precedes interoperability. Now, that means what are the preconditions for interoperability? There needs to be an agreement with the basic abstractions like what is a simple feature, what is a relation, and there needs to be a closed set of operations like join, select, project. What's the situation in Earth observation data? Well, there's no agreements with the basic abstract. There's no agreement even what a data cube is. And of course, that's the good side of things. They're open-ended operations. People kept developing new models all the time. How can you standardize things which are open? And in fact, they do so with incompatible implementations. Ryan Abernathy said that recently, even between PanGL, there are incompatible implementations. And of course, people have the right to do what they wish. Some people like to do two-dimensional convolutions in space or compare data in space. I'm the one that works on time series, and we both have the right to exist. This, of course, translates into a huge amount of different types of training data and different types of machine learning, deep learning models. Pick my guess. So are you going to standardize things which are open? And of course, people will not start doing 3D models. And the older people like me here in the room have probably learned a thing or two about APIs, good APIs like OpenGL from Silicon Graphics or good APIs that we had in the good times. Now, the new generation of Python people thinks computer started with Python. And then their aim in life is developing some programs using X-array. Now, X-arrays are so good that they're bad. Why they're bad? Because they ensure maximum flexibility, but there's a lack of consensus API. I went to a page of an application, which is very popular in this community, who has said, well, this is some examples of a toolkit to learn, and okay, this is a model like this, and give me the model. These are 500 lines of code in Python. Who on earth but the developer can understand that code? Oh, I have a new deep learning model, 600 lines of code in PyTorch. Thank you very much. How can an end user, a real end user, not you, the programmer, learn it? So no wonder, after some hundreds of millions spent on developing situation for European community, my friends in Brussels are still sad that most everyone is still using Google API, Google Earth Engine. Why people use Google Earth Engine? Because it has a nice API. And the API, and this is like, you want to do things like, instead of 300 lines of code, you want to do 1 line of code, train my model, and 1 line of code, classify my model, 1 line of code, label my data. That's what you want. You don't want 500 lines of code of PyTorch. So APIs are user-focused, they make simple scripts, they have rapid results. Okay, they're more rigid, but users love them. Now, I can hear you asking, wow, is OpenEO the way to full EO interoperability? Because I hear a lot of that. No, sorry. OpenEO is a very interesting design, but it's an open design, which its primary aim, in the end, that's not what you talk to the old guys like Edzer, who's a good friend of mine, says, but that's the practice. It's aimed to enable competition between private and public cloud providers. It's Europe's answers to Google Earth Engine. It's so open that if you think of it from a private company point of view, or even a provider point of view, the idea is that you have a backend, and between the clients and the backend, that sits an OpenEO API. So imagine you're company A, and you develop a killer application for a certain area. And then you're company B, and you say, why? Why should I develop the same application? He's already milking money out of it. Oh, I have to develop service B, which is better than service A. And then the third company comes, why should I develop a service B or service A? I'm going to do service C. And by the way, all of these are going to be proprietary. So what's the interoperability there? OpenEO is good to promote innovation and competition, but really not good for interoperability. And of course, I said there's a good side to this. So when you go over it, you say, okay, what can anyone do and what can this poor guy here do to help it? Of course, we have now help from, of course, the European Commission. Who else? And the European Commission is funding a project called Open Earth Monitor. And basically, one of the outcomes of the Open Earth Monitor is that we're building a bridge between OpenEO, which is, you know, and SITS, which is the time series software which I've developed. And this bridge will allow users from OpenEO to use SITS. That does not mean that other applications of OpenEO will be able to do the same kind of time series analysis we do in SITS. That only means that anyone who has a SITS backend can access it via OpenEO without installing R, RStudio, and so on, because that's what OpenEO does. So then, for example, he can benefit for things like we do, like it's now state-of-the-art, like the object-based time series analysis with spatial temporal segmentation. So now, instead of having to install R and RStudio, you just write 2 lines of OpenEO code, and hello, you get your object-based image time series analysis. Which means that this is what we can do. So, interoperability in big old data is unlikely to happen. There's, again, Hayan Abernathy was here a few minutes before and said you cannot even achieve open interoperability in big EO data with inside the Pangeo community. Because there is no interoperability with R scripts, with X-array scripts. interoperability, POSIX, 9 intersections, simple feature, RDBMS, is about closed, clean, effective APIs. It's not about give me your X-array ZAR desk code, and I look at 500 lines and I say, well, how do I do this to my problem? No. So get over it and think about. Now the dilemma becomes different. Cooperation or competition? Competition is fine, will provide advances, but for the happy few that can pay. Like I said, I'm here on behalf of the 85% of the unhappy, a lot. Which means that I'm into, and I think we all that care about the planet should be, in favor of cooperation for global benefits of Earth's observation. With that, I close. Thank you very much.
Okay, we have a few minutes for questions, if there are any from the audience. Yeah, I don't see any. So my biased perspective is naturally, as the OGC is a consortium that tries to build the interoperability. What will be the guidelines? Because I understand that, well, the full interoperability is probably hard to reach, because it's also like we are in the science still. Maybe this is the phase. But what would you recommend in terms of this global community?
I mean, how can you build into... Okay, there are two issues here. The first issue is the basics. The theory is in a state of flux. It's not frozen like the simple feature. Now, simple feature did wonders for OGC, right? But you had Egenhofer coming first with his 4 intersections, then 9 intersections, the 9 intersections, dimension extended, and on top of that, you say, okay, now I have a simple feature. Which is fantastic. You have wonderful, wonderful job with the simple feature. So what is the equivalent of that in deep learning for Earth observation data? Is 2-dimensional convolutions, or 3-dimensional convolutions, or temporal convolutions, or attention models for time series, or attention models for whatever. I mean, every day there is a paper coming out on any journal saying new things. My TOEIC to OGC is don't promise what is impossible to deliver. I think it's impossible to deliver. It's possible to deliver, for example, a standardized things in stack, but still the names of the beds in stack of Microsoft Planetary Computing are different from the names of the beds in stack in, for example, harmonized Landsat 6. There's no even harmonization on the names of the bases. So I, for one, have given up any hope on interoperability. And I'm focusing now on saying to people, perhaps OGC could come, but that would take time and would take selfishness, unselfishness from the community that would require people who now do Pangeo, who do a lot of these things, coming up with APIs. It's not late enough to realize that your 500 line of PyTorch code may not be what I need. You might give me an API that says, classify this data using this model. But people who are not, young people especially, love to say, this is my fantastic ZAR desk X-array code. Fantastic for you, not fantastic for the users. But this penny has not yet dropped in this community. It is my job, as perhaps the older guy here, oldest around here, to tell you, your penny needs to drop. You need to understand that what you're doing is fine, but it's not what the global community needs. And at that moment, you view things differently.
Okay, thank you. Yeah, we may need to talk about that more
okay.
and more.
Thank you very much.
Thank you very much again. So now welcome Wolfgang Wagner from Technical University from Vienna. We'll talk about the federated scientific infrastructure and services for the cross-domain applications of Earth observation and climate data. So welcome, and your floor.
Thank you for the introduction. Of course, it's now very difficult to talk, also should be a very clear message, because I personally am a bit more optimistic than he would be. And I think we also can be optimistic in terms of how we make steps towards federating scientific infrastructures and services so that we can have cross-domain applications for Earth observation and climate. So first the question is, why do we need big data platforms? I think so. This is obviously at the heart of this conference, and there have been much discussions, of course, about big data platforms. And the reason why we need it, because there's been such a rapid growth in the quantity and quality of observations and model simulations. And what we've seen in the past, that the data transfer capabilities have not grown as fast as data storage and compute capabilities. So that's a technical reason. Another reason is because that was also nicely really highlighted in the last section. We tend to do the same things, just a little bit different. That means we're very inefficient in the way of how we handle our data, how we store them. And obviously, if you think about energy savings, it would be much better to have like a good repository of data, and where people would work jointly on this. So we have the paradigm to bring the software to the data. But at the same time, we can note that many of the initiatives that have been started have failed. So there certainly have been some ideas to build monolithic cloud platforms, and they've been promoted a lot also within this conference, for example, but they never attracted enough users to make them sustainable. I'm, for example, thinking about here the ESA diocese that failed to become sufficiently, to have a large number of users to become self-sustainable. I also find it very interesting to notice that the Google Earth Engine, obviously it's still the most powerful platform we have out there, still obviously with the largest numbers of users that is out there, but you start to see like the critical comments even in the literature. For example, here a review on the Google Earth Engine where the authors conclude at present the development of Google Earth Engine is still in its infancy. Well, other cloud providers would say, well, we would be happy if we would have these kind of similar capabilities. And I could also quote one of my PhD students saying, oh, it's so inconvenient to work on the Google Earth Engine because you can't do the stuff you really would like to do, but you're bound by constraints of these platforms. So what has been overlooked? Well, I think one thing that has been overlooked is that the large majority of the users just work with very small data volumes. So for them, downloading data and then working locally with this is really not a problem. I'm talking really, I think, at least 95% of the users. So that will not change. And then there are other users who work at continental to global scale, so they work with petabyte scale data. But these don't give up sovereignty and easily move to another platform where they have no control over. The other thing that has been overlooked is, I think, it's not the IT. It's the data where people go to. So if you had some of the successful initiative in Europe in last time, in recent years, those that were successful was because they had good data, why people went to them and worked on the platform and using the data. So if you want to have a successful platform, offer the best data which is out there. And I think the last point I always said, like the diversity and complexity of scientific algorithms calls for very flexible solutions, so as long as you always constrain the users, you're not making them happy. So that means that there's no monolithic solution that can do it all. I'm not saying that some of the solutions can be very attractive and fulfilling the purpose, but there's no solution that can do everything. Let's come to the point of federation. When we started working in domain, for us, the idea of federation was always on our mind, and maybe motivate this a little bit, as you're here in Austria, in the beautiful city of Vienna. Well, we are a small country with 9 federal states. We have 22 public universities, and they're all independent. So you cannot enforce anything on them, but you need to bring them together towards federation. And if you think about how Austrian infrastructure has evolved is, that it was always initiative of like one university or group to say, well, we need to, for example, build a good scientific network that started developing, and then it is grow, and people's and different organizations started to join, so that we have now an ACCONet that's organized with members from all universities and many different research organizations to have like the backbone of our scientific internet in Austria that's connected to GÉANT. Or we have the Vienna Scientific Clusters, an HPC platform that has also grown very successful from a few partners, and it will soon become the Austrian Scientific Cluster. A bit in the same tradition, we thought about how can we scale up our Earth observation capabilities, and that was part of like the recommendation of an Austrian expert group who said, well, you know, don't try to build a monolithic solution, but try to build of what's already there and develop a cooperation model. And the way how we started the whole Earth observation data center, the EODC, was by looking at the cooperation model that was already established for an open source development community, and we adopted it to our goals and needs. And we basically shaped it by legal considerations so that it really fitted. And this was founded in 2014, and the mission statement of the EODC is to work together with its partner from science, the public and private sector, to foster the use of Earth observation data for monitoring of water and land. And our vision has always been that we didn't see like one big data center that's growing, but a couple of data centers that are well connected and services that start to be interconnected. And for us, it was always Austria being small. We always wanted to have like an international partnership in there. So what we have now built up over the years is that we have built a collaborative infrastructure where we have hardware co-owned by multiple organizations, so that basically you can build bigger things and like, for example, storage, and everybody pays into the pot, and then it's much cheaper and you get more terabytes for your money. So we've built a petabyte storage, we've built up the gigabit Ethernet to connect all the different parts. We connected to supercomputers, we developed a cloud platform, we have a tape backup, we have near real-time operations. So everything you need to do scientific work in an infrastructure and to do also operational work. So just to talk about the infrastructure, for example, what we're doing with it, we are doing global flood monitoring using Sentinel-1 in near real time. So we fetch the data that become available on the ESA data hubs with a hub watcher, and then process the data, pre-processing and the analysis of flood as soon as possible. And I think it's a very nice number here, for example, that within less than 2 hours, you come from the data becoming available on a hub to being presented to the user. One nice example was where the system really proved very useful was for monitoring the floods last year in Pakistan, and we have done recently a paper by Florian Roth and Natural Hazards and Earth System Science that give you the number of this incredible flooding. Well, we didn't stop at the Earth observation part, but the next step, we as Earth observation people always use climate data. Climate people use also Earth observation data, so the next logical step was coming together with the climate community and building like joint infrastructure that basically meant we strengthened our connection with the Austrian Met Service, that is now called Geosphere Austria, who also have like near real-time capabilities and supercomputing capabilities. So we developed a whole role model around this. Yeah, and I think that project that was led by University of Graz was particularly nice because it established a functioning governance model for infrastructure development that goes like this. The scientists say what they need. Then there's different IT units and different organizations making a proposition. Then the scientists make a selection, and then it's being implemented by those IT units that have basically made the best offer. So that's how we advance. So we also allow competition between the different infrastructure providers that are part of that network. And now, as this was very successful, we started in our last project called Cloud for Geo that is coordinated by myself and Matthias Schramm, that we start connecting additional partners and basically have in focus the core services that are out there, like supercomputing, like fair data repositories, and we tried as our best to connect it, for example, to the European Open Science Cloud, EGI, and of course to Copernicus platforms and Destination Earth. So what are the guiding principles for this development, infrastructure developments? Well, we are now open for all users for geoscientific domains. We start very much from the data and the scientific ambitions. So the question is not what hardware do you need, but the question is what data do you have and how do you use it? So it's like really looking at the data management plans. The next idea is that we want to strengthen all the collaborative data core facilities that we have in Austria. So that's the internet, it's the Vienna Scientific Cluster, EDC, Federating repositories. And we always have this, this trick in there that if people put money on the table, that we use 20% of that money to buy hardware that goes into public use. So that we, for example, have like a joint shared repository. And very importantly, we want to connect to the European infrastructures like EOS and EGI. And of course, open science. So I was really happy about the session today in the morning. It was really great. And well, the vision is to go towards building a web of fair data and services. So when I look back, we always had this federation in mind, but 10 years ago, it was really difficult to achieve. Now with the great progress that we're seeing, like done by organizations like Pangeo and EOS and EGI, that we really start to have very powerful software that can allow us to have multi-site platforms. So I think we can actually build this federation. We don't necessarily need to standardize everything. And my recommendation is to move fast in the field of Earth observation, is that this community think more closely about collaborating with EOS and EGI, that this community promotes the collaboration between platforms and not say, here's a solution, and well, let's connect them. Reward the work of data scientists, data stewards, and open source community development efforts, and give the scientists the choice to work where it's best for their applications, either in terms of quality of the service, quality of data, cost, sustainability, governance, legal aspects, etc. So don't enforce them to work on a particular place, but let the choice open. Thank you very much.
Thanks for this quite deep insight in the platform. And the questions from the audience. Okay, so well, I wonder how do you envision that integration with this European platform? On which level actually you're going to integrate with them? Do you have already any kind of ideas?
Well, in the end, we, for example, would have money to actually buy hardware to put it physically somewhere else to be more closely connected to these infrastructures, if this is necessary. So that, for example, you, in a way, like building a bridge to those.
Okay, but also your services are going to be provided in this Destiny E, for example?
Yeah, we are working on this.
Okay.
That basically we're also adopting, for example, OpenEO ways so that we can start connecting different platforms and optimizing workflows between the different platforms. And then it's really up to the service that you develop which component of the service is. And in the end, most of the data that come out of public data sets anyhow end up in the repositories like the data lake.
Yeah. Okay. Any other questions? We were all shortly over time, but
yes.
Thank you very much. Thanks again. So now welcome Jonas Eberle from DLR, and he'll talk about the development of the DLR exploitation platform called Terabyte. Welcome.
Thank you for the introduction, and welcome to my presentation. We've started at the German Remote Sensing Data Center at DLR 4 years ago to build up another new platform dedicated for Earth observation data analytics. And in this presentation, I'd like to summarize a little bit the experiences and the challenges that we had. Of course, you might now think, also after the presentations and discussions today morning, that it can be another monolithic system. Of course, we also need to talk about a federation. I will come to that point later in my presentation. So first of all, when we started 4 years ago to think about building another EO exploitation platform, We, of course, look at our users, primarily DLR scientists, but also project and collaboration partners, what they already use and what kind of use cases they need. We have a lot of scientists doing global research based on different kinds of Earth observation data, all the sentinel data set, Landsat, MODIS, VIIRS, and so on. And many of them using different kinds of infrastructure. We have users that use Kubernetes workflows. We have users that use just virtual machines. Of course, we also have users that make use of the Google Earth Engine. But also we are involved in defining and producing global analysis-ready data. We have other users that do climate modeling already on HPC systems, and we need to we wanted to build a system where we can support different kinds of infrastructures and workflows. We have a lot of money that DLR has invested, around 16 million euro in hardware, so we can think about whether to go to a commercial cloud provider, doing something on-premise outside the DLR, or maybe also doing a collaboration with other data centers. And this is the solution that we took. So we have now a collaboration with the Leibniz Supercomputing Center, located in Germany, north from Munich. And we've built together with them an on-premise infrastructure with and at the LRZ, because they already have decades of experiences in operating and maintaining, setting up large-scale infrastructures and large-scale data storage systems. So we are flexible in the infrastructure setup. We have in-kind contributions from the Leibniz Supercomputing Center that maintains and operates the infrastructure, which makes it very cheap for us because we only need to pay for the processing hardware, this data storage, and of course we need to handle EO data management on our own in comparison to go to some DS platforms, for example. But with this investment, we got a lot of hardware. So we have thousands of CPUs available, hundreds of GPUs. We have 50 petabyte of usable storage, all of them with a minimum lifetime of 5 years. And they are there. They can be used 24/7, and we and our project partners can make use of it. Of course, when building the system up, we started first to think about how we catalog all this kind of data. I've mentioned we started 4 years ago, and stack metadata was not really mature at that time. It has become mature in the last years, but we were ready at the time where we say, okay, we can look at OpenSearch again, but now it might be better to work with Stack and Stack API, and that was really the right approach. But then thinking about how to ingest the data that we have, that we want to provide, how we catalog the data, and there are additional challenges we have found out. So the first challenge is that there are unfortunately inconsistent EO data inventories. If you look to different kinds of platforms, to different kinds of data providers, because you need a way to get the data fast on the platform, and that's often not that easy. I want to show two examples. It happens that scenes are being removed because there are a corrupted product after they have been published. That's an example of a Sentinel-2 scene from June this year, so not that old, which has been removed from the official, at that time, Copernicus Open Access Hub. They have an interface where you can, or they had an interface where you can query what kinds of data has been removed. Unfortunately, that's not yet available in the new system, but that's very important because if you look for these scenes at the Copernicus data space ecosystem, and I think also on other platforms, the scene is still available. So we need to have a possibility to identify and keep track of removed scenes. Also within collections, there are reprocessing of some scenes because the metadata is maybe wrong or the data product is a little bit corrupt. So there can be multiple versions of the single acquisition. So we found out for Sentinel-1 SLC, for some scenes, there are up to 10 reprocessed scenes or reprocessed versions. And both, for this example, both versions are still, or two versions are still available in the official data hubs. So that's, of course, also a problem for the users who want, for example, to do some time series analysis. They need to keep track what is the latest version of this individual acquisition. Of course, this is a point where we as a platform provider can support the users to identify duplicate scenes and only make the latest scene available. There's also one good example from the NASA Alaska satellite facility, also having a replica of Sentinel-1 data. They keep track of this. They only have always the latest version of a single acquisition available. Now, if we have, so we have built up an inventory to keep track of the changes. Now, of course, the question is, how do we get the data into our platform? Or maybe how to efficiently download petabytes of data, which still can be handled at the moment. And in some cases, it is also often necessary. But here comes the next challenges. Downloading data as a regular user, not as a privileged user from the Copernicus data space ecosystem, allows you, that's a screenshot from the quotas, allows you to download 6 terabytes in a month. Okay, that's not so much because we have more than 16 terabytes a day of new Sentinel data. So as a regular user at least, you cannot download the complete archive unless you create 70, 80 user accounts, which nobody wants. But another example, as I said before, Sentinel-1 data set is available also on the NASA Alaska satellite facility on Amazon Web Services. Per default, there's no transfer limit. So NASA has a monthly limit, but you can communicate with them when you want to download large amounts of data. And I did this and downloaded 100 terabytes a day as one of the examples. But of course, downloading petabytes of data with new satellites coming up in the future, Landsat Next, NISA mission, and so on, it is definitely not feasible in the future. So again, we need to talk about data federation, and not only talk about, we need to implement data federations. And we have started collaborations with the USGS and also with the EODC data center in Vienna to tackle these topics. Now again, we have the data on the platform. We have a catalog for the data. Of course, we are building services on top of it, data discovery, data visualization services, data cube services. At the end, the user wants to conduct some algorithms with tools like Jupyter Notebook, the Pangeo software stack as an example, OpenEO. But we have also other users, as shown in the beginning, that want to make use of HPC computing as an example, or just want to run some command line scripts. So we thought about how we can keep with these different kinds of infrastructure requirements. So we are built up like a little bit like a hybrid solution. On the one side, we have an HPC system, and on the other side, we have a cloud system, which is not externally in the cloud, but is an on-premise cloud system. Of course, the cloud is based on containers and Kubernetes, And we provide mainly the web services that runs 24/7. On the other side, we have our processing system where most of the compute resources are available with a job scheduler again, and where we have applications like Jupyter Notebooks, QGIS, and RStudio available right away. At the end, web service also calls then the batch processing system. I have here some screenshots, so the user has also a web portal and can launch the interactive services, like a QGIS in a browser or a Jupyter Notebook. So to conclude my presentation, I have some recommendations. So we should also think about, and not only think about, work on providing stack metadata with the original Earth observation scenes. We should establish federated data holdings to minimize data copies around the world, also to tackle the problem of inconsistent inventories. We should also work together for common architecture, so sharing resources of developing components for platforms. There's later on a presentation about the common architecture EOEPCA. And finally, we need to provide consistent EO data inventories, for example, also with notifications for deleted and replaced scenes. Thank you.
Okay, we are probably a little bit late, but if there are any questions from the audience, to Jonas? I don't know. I had one particular thought about the invalidation. How does it affect actually products? And especially if we are talking about federation and all of that integration. Very shortly.
The validation, you mean?
I mean, the invalidation of the scenes that you mentioned in the one of the slides that you have, like...
Oh, yes. So, of course, I think there needs to be some kind of a central curated data inventory where all federated partners would need to comply with. I think that would be the best aim from my perspective.
Okay, thank you. Any other questions? If not, thanks again, Jonas.
Okay, then I'm happy to announce the next speaker, Roberto Ugolotti, and he will take us on a journey over the open source software landscape at the GRC Big Analytics platform.
Okay, thank you. To be honest, I wish I had the opportunity to change a bit my presentation while listening to the others, because I think this session is really becoming like a talk from the general to the particular, because I'm also presenting another, let's say, big data analytics platform, the ones that we are using at the JRC. And I'm going to present a little bit on what we do with open source and draw some conclusions that may be some of them may be simple, but some of them may be interesting considering also what has been said so far. As I said, I work for the Joint Research Center. We are one of the co-organizing the event, and we have a booth outside if you want to know more about what we do. Basically, we have several hundreds of researchers working on many different topics. So they need a lot of data and they need a lot of processing and computing power and environments. And so this is the role of the Big Data Analytics Platform, which is let's say an on-premise cloud platform that serves the needs of the researchers of the JRC. This is just some number to give some idea of what we do. We also store some petabytes of storage. We have some servers that can be used for HTC, for GPU processing, and et cetera, et cetera, et cetera. Basically, everything that we do is based on open source software, from the operating system and the storage, the monitoring, and also the services that we provide to the users and the software that the users are allowed, that we provide to users so they can use to do their daily work, let's say. We provide, let's say, the whole data life from data ingestion to the data processing that is done by us, for instance, in case of pre-processing, or by the user themselves that generate new data that can be shared as it is, or they have some models, or they produce some dashboards, something that allows other people, external people, to analyze their results. And for each part of this, obviously, most of it is based on open source. So for instance, one of the main, let's say, way in which our users access to our services through Guacamole, so through a web browser that give access to a fully remote desktop environment in which they can access Sentinel data or whatever kind of data using the software like QGIS or Python libraries, etc., etc., etc. We do not only use open source, but we also provide back some libraries, some tools to the open source community. We publish mostly on GitHub and on code.europa.eu, which is the repository for all the open source software developed by the European Union institution. These are some examples of the JRC. The last two are PyGeo and are developed by our team, by BiDS team. And one is PyGeo, which has just been presented in the demo area by Peter Kempeniers, and Voice, which is mostly for dashboarding, to create dashboards to make data available to the public. This is a graph that is very, very similar to what you just saw in the previous presentation. We collect data, big data, but also small data, because basically we, let's say, answer to the needs of our researchers. We are strictly in contact with the researcher that use our data and our environment, so we collect data from various providers. It can be both recurrent downloads or even some historical downloads, let's say once only once done. And we collect also the metadata, which is provided in a Stack, which is collected in a Stack catalog, and so can be queried by our users. So users have, let's say, one interface to many different collections, let's say. And all this workflow, all this data ingestion workflow is based on open source software. So we do data retrieval through EODAG. The DAG library was also presented yesterday here. We store data into our file system, which is called EOS, provided by CERN. We do some post-processing with our library PyGeo. We use Stack for cataloging, Elasticsearch for storing the metadata, and OpenSearch to manage download logs. And we also have a web data catalog, which is based on the Stack browser, and we provide access through the APIs, the fast API on the Stack, so for users. A very quick word on the libraries that we are using. One is PyGeo, as I said, has been already just presented right now by Peter, and he's here if you have any additional question. I think this is an open source image processing library in Python that is fully open source, released under a GPL v3 license. And it is interoperable in the sense that you can easily retrieve data using its Stack interface, and you can bridge it to NumPy, XArray, or Pandas without memory copies, so it's quite fast. The other library that I want to briefly introduce, there will be a link in the next slide, is Voice, which is based on Voila. Voila, in case you don't know, is an extension of Jupyter Notebook for standalone application and dashboard. Basically transforms your Jupyter Notebook into a web page. Basically, they render, they hide, let's say, it hides the cells with the code and shows only the results. And mostly my colleague Davide De Marchi, he developed this library, which is called Voila Simplification, because it's quite complex to use by itself, and so he created some, let's say, high-level library in which you can transform easily your notebook into a dashboard. The code is available online at this link, and also the documentation is there. These are just a list of the main features of this library, not going into details, but in case you're interested, as I said, there's documentation and the full code is online. This is just an example of, I mean, it's not just a simple list of commands that are rendered. You can create very complex dashboards, and they are connected and read data from any different sources because it already has an integration with a libraries that allows you to retrieve geospatial data. Last thing, we also promote and provide open data. So most of our users at the end generate products that we host and publish. So we have a JRC data catalog, which is public, and it stores more than 100 terabytes of data that is generated by JRC itself. And also, actually, here at BiDS, we are going to present a few of these data sets or the work that are based or that generate this kind of data. Just a couple of words on, on the advantages of using and contributing to the open source community. Most of this has already been said during these days. One thing that I would like to highlight is that you don't have to pay for it, which is simple, but sometimes we forget about it. And the other point is because we're talking a lot about interoperability, and I think we mostly think about machines, but I think that using standards, using open source libraries, using open source software is not only an advantage for the machines, but also for humans, for programmers, because when you jump into another environment because you change work or because you have to cooperate with other people, if you use the same tool, it's easier to do that. So I think this is an advantage that maybe sometimes is a bit underestimated, the fact that you can be productive as soon as you join another company or another environment just because they use the same tool. And these tools usually have wide community, and so they are frequent updates, security updates, bugs solving, and also they are transparent in the sense that even if it's not easy, you can reproduce what they do, and you can see what the thing that they did was done. I'm finished my time, so very quickly, just using a completely open source, you have some difficulties in the sense that sometimes these library change the key features, so moving from community to enterprise edition, and you lose some abilities of doing things. Changing in licensing also sometimes gets closed immediately. And it's a bit more difficult than, let's say, a completely standalone environment, because you need to manage compatibility between all the different versions, all the dependencies, especially when you want to keep up to date the results. And okay, I'm finished. I'm just skipping the last one. Thank you.
Thank you, Roberto, for a nice presentation and keeping so much in time. So we have time for questions and discussion.
Hello, thank you for your presentation. In fact, I have two questions. I came to this conference to clear something from this lot of new topics and names, and I must confess that I am getting more and more confused. For example, your first slide, your Joint Research Center, you are bringing data from Copernicus. What does it exactly mean? Do you take the data from the Sentinel satellites? Do you take the data from Copernicus 7 services? Why do you take data from Copernicus, your Joint Research Center, and we already have 7 services and we have data from satellites? And second question is, I'm not from a Python community, I'm from our community, and I will give a question, but I think it's the same. This is an open source project, and you mentioned there is a problem between dependencies in the software. Why do you publish your code only on GitHub, not on these repositories where these dependencies are tested before putting. For example, in the R community, this is CRAN or bioconductor or whatever. And the GitHub is only like a beta version or something that is still under development. Sorry.
Okay, so about the first question, we download the data because at the end you get really terabytes of data, and so you cannot download it, you cannot expect our user to download it every time they need it, because otherwise it's unfeasible. So when our computing environment is physically closer to the data itself that we have downloaded, and also is curated, is cleaned, is post-processed, and it's the same for all of them. So this is the main advantage of doing that. And regarding the second point, it's not only about Python and R, because for that kind of part, also for Python, you can manage more or less. It's everything else, also from operating system level or databases or everything like that. It's not only for libraries for processing. It's everything that stays behind. Python and R is what our users see, which basically most of the time is left to them to deal with this issue. What we have to do on the back end sometimes is more difficult, because we have at least 3 or 4 different Linux versions, let's say. We have different drivers. For instance, we have GPUs, so you have drivers. And so it's not only that part, which is probably the simplest one, let's say. The hardest part is really to have everything up to date, mostly for security reasons, and also to allow users to have the most recent updates, etc. But this is mostly for, to keep everything running, because we provide many different services, and everything must run with everything else. So it's not only a matter of Python and R. I hope this answers your question.
So thank you very much.
Thank you.
So our next speaker will be Richard Conway. He is talking about an open source EO data exploitation platform with a very difficult to pronounce acronym. So I'll leave it over to him.
Thank you. Good morning. I guess I can help with the acronym. So we pronounce it EOEPCA, which is EO Exploitation Platform Common Architecture. It's a project that we've been running for the last few years, an ESA project. So first, from our perspective, what is an exploitation platform? So we define it here. It's a virtual work environment, a cloud environment where expert users can access data, develop algorithms, and do their analysis and create value-adding outcomes, value-adding data. But also to facilitate the sharing of data and applications, and to try and create sort of communities around that. There's a sort of a new term that perhaps has emerged recently also, which is information factory. And we provide a perspective here really on that from an exploitation platform point of view. So the idea of the information factory is to transform the data into actionable information. And so what we try to do here is define the broad capabilities that are needed to do that. So we have some infrastructure, the cloud environment that has storage and data and compute. We need to discover those resources, the data. We need to then process that data, initial processing, pre-processing perhaps, into higher value forms, analysis-ready data or data for machine learning. We can then transform it again through data cube interfaces and through machine learning. But ultimately, we need to present that information. So we have clients, and in particular, interactive dashboards that can make that information more easy to consume for decision makers who don't want to get bogged down in the details of the science, but they want to be able to make their decisions on easily digestible information. There's another dimension to this, which has been well expressed already in this session, which is around interoperability. There are many platforms, we know that, and so the idea of the common architecture is to try to facilitate interoperation and federation amongst these platforms. So the approach we're taking is 2 parts, really. to define an architecture, a reusable architecture defined around open standards as a facilitator for the interoperability, but also to create a reference implementation of that architecture to help to refine the architecture and to get feedback on it. But also, importantly, to contribute to the open source ecosystem of tooling by making our components reusable and contributing to that community. So this sort of summarizes that approach. So we have a number of partners in doing this, what we called our domain experts, so Demos, TerraDue, GeoLabs, EOX, and EO Farm. And together, we have created the architecture and an implementation of those building blocks that we've defined. So what I'm going to do is quickly walk through the essence of the key building blocks that we have in that architecture. So I guess perhaps right at the heart of that is the ADES, which provides hosted execution of user-defined processing. So this is speaking to the bring the processing to the data. The data is in the cloud, the compute is in the cloud. You have some perhaps very specific algorithms that you want to run on that data, and you want to be able to push that into the cloud environment. A key feature of this, it builds upon the OGC API processes standard, and in particular, the draft part 2, which defines the ability to perform user-defined processing. In particular, this user-managed application cycle, which is the ability to deploy an application into a platform, to discover applications, execute, monitor, and then obtain your results at the end. So some key features of the approach offered by the ADES and by the OGC standards are using Stack for input and output of data. This creates a sort of a metadata abstraction, and this aids portability of the applications. We also are aware that for efficiency, we need to make good support of cloud-optimized inputs so they can be accessed directly rather than it being a requirement for those to be staged in by the platform. We also have abstracted the execution of the workflow itself, the processing, so that providers, so our ADES is extensible, so out of the box we provide a runner for the execution of the workflow in Kubernetes using a tool called Calrissian. But due to the way it's been designed, you can plug in alternative implementations, alternative runners of those workflows. So a key feature of what I've explained there about the processing environment is the idea of an application package. This is defined by an OGC best practice for application packages. And what is it? What is an application package? Well, it's designed to be a self-contained, independent representation of your algorithm, of your application, in which all of the dependencies are packaged together. How is that achieved? Well, I guess there are two main parts to it. In terms of portability, so the idea is to make the applications portable so that we get this idea of interoperability. So the key features there are use of the common workflow language to define the workflow and to describe the application, and then typically using container images to define the steps of those workflows. And then Stack also helps to provide that abstraction as well and make it more portable. So the container images define the steps where your application code, and at the top of the graphic there, we can see that can be anything you like, anything you can put in a container, you're able to bundle your application. And then the CWL document that accompanies those containers describes the workflow in terms of the steps, but also importantly how to invoke the workflow, i.e. the inputs and the outputs. It also inherently within CWL supports various patterns to parallelize that, different scatter patterns. But the whole idea of the application package is, as a unit, it can then be deployed to an OGC API processes endpoint, and then you can consume it. You can execute your applications. And I mentioned the best practice there, which is a published document. It describes the profile of CWL for application packages and how Stack is used for the inputs and the outputs. Okay, time's running out, so I'm going to speed up a bit. We have good adoption for these application packages. So there's a list of companies here that are currently exploiting this technology. So Advasio, EOX, NASA, Petabyte, TerraDue. So TerraDue have a great support here. They've been very much a driving force in support of this approach to define the application package approach. But you know, there is an ever-growing list of companies embracing this approach. When we think about processing, we think about we need to handle the results of the users. So this gets us into resource management. So users need to be able to establish object storage. They need to provision their data into the storage, output from processing, for example. They need to register their assets so they can be discovered, and they need to make that data available for retrieval, visualization, exploitation. So this brings us on to our workspace component, which really brings that together either as a user or a group or a project. It creates a space for your resources. It comprises a set of sub-building blocks effectively. So we have resource discovery, we have data access, we have resource registration, and the object storage and container registries that are needed to actually host the assets. And the Workspace API provides an administrative interface that allows the creation of workspaces, the instantiation of them for user groups and projects. So tunneling in a bit more, then we have these resource management components. Again, the key features here are standards. So we have the resource catalog, which provides OGC standards and Stack and OpenSearch. And it's a key point, it's not just about data. There are other types. So there are application packages. There are services, such as processing engines and other catalogs that you may wish to discover and interoperate with, and pre-deployed processes that can be regarded as resources to be invoked. Data access services, again, the typical OGC standards that are provided with access to the assets that can be in object storage or other systems. And to provision these environments, we have a registration API for ad hoc submission of records into the system, but we also have a harvester that can harvest external catalogs, typically through Stack and OpenSearch. The application hub provides an environment really that can support two things really: developer tooling, web-based developer tooling. This builds on Jupyter Hub and extends it to help them create their application packages. So there are a number of applications that already exist. But also it gives the opportunity for users to create their own dashboards. They containerize them, they can submit them into the application hub, and then those applications are available for integration with their other services. So they can write interactive dashboards that interact with their processing to maybe perform ad hoc execution of analysis to present interactivity to the decision makers. So pulling all of this together, so I've described building blocks and they all stand alone. They can be used individually if that's what you need, but we've also designed them to operate as a coherent system. So very, very quickly, we can harvest resources. We can perform processing. We can push the outputs of our processing into our workspace, and then we can exploit those outcomes, either using data that's already there and displaying it and visualizing it, or performing ad hoc processing in response to interactivity via the dashboards. All of our work is open source, it's cloud native. We typically run our environments in Kubernetes, so we have Helm charts, Docker images, etc. Time is sort of out, so I'll perhaps just leave you with one. We have a number of operators that are listed here that are picking up not only the application package approach, but also various others of our building blocks. They're taking them into their operational platforms and they're providing us feedback from real-world experience. So final slide is just in summary, all our work is open source. We put all of our developed code in our GitHub, but we also have contributed to and support a number of existing open source projects, PyCSW, the Zoo project, OWS Lib, and there are others. So it's all in GitHub. Please visit our GitHub organization, and we also have a website there. Okay, that's me, thank you.
Thank you very much. Is there a question?
Thank you very much for the talk. I have a question about the user-defined applications. How do you handle it? I guess there's a certain security risk for the backend provider. Is there any way, would you recommend to handle this? A code review based, or if I want to submit my code now to a platform? Is there something in between?
Yeah, I guess that's a good question. Speaking honestly, it's not something that we've particularly tackled in terms of the work that we have done and the design that we have. I mean, what I would say, we are not providing a platform. We're not running a platform. We're trying to create an approach and a set of building blocks that can be picked up by platform providers. So in terms of governance, let's say, around what is accepted into the platform, I would slightly slope my shoulders on that right now. Although I do take it's not the first time the question has been asked, but it's probably a question that we should take away and understand if there are things that we can do within the architecture, within the approach that actually would address that. But in the end, the platform provider would it be expected to establish their own governance about how they use our building blocks, how they put them together, and how they accept new applications into their platform environment. And also how they sandbox, let's say, ring fence the execution environment of a given application so that it cannot, from a security point of view, do anything that it shouldn't do.
Thank you.
Okay, thank you very much. In order not to eat too much into our lunch break, thank you very much for this presentation. So our last speaker for today is not Lorenzo Bramante, but Chiara Liuzzi will jump in and she will present the Italian data center for EUCLID data.
Hi everyone. I'm Chiara Liuzzi. My name is not in the ones listed in the presentation because I actually don't work for this project, but unfortunately my colleague today is sick, so I will try to explain his work on behalf of him. We both work for the data processing systems and scientific and technological application at Altec that is mainly based in Turin. I mainly work for the projects that are based on artificial intelligence, but the rest of my group mainly work on projects based on the data processing of ground segment data. So today I will present this work that is based on the SDC-IT-PROD, that is the Italian data center for production of EUCLID mission data products. EUCLID is a mission designed to better understand the dark matter and the dark energy of the universe, and I think that many of you yesterday saw the first beautiful images that they released. The satellite was launched in the early July 2023, and it will acquire data for 6 years of nominal phase, and then there will be other 2 years of post-processing. During all the years of the missions, the data that will be sent to the Earth by the telescope will be managed by the ground segment of EUCLID. It is composed by 2 main segments, the operational ground segment, which includes the ground station and MOC that is located in ESOC, and the science ground segment, which includes the Science Operation Center and the various science data centers that are 9 in total and are distributed across Europe and the United States. We can say that the main component of the consortium is represented by the SOC because it contains the EUCLID archive system, but in particular the science archive that will contain all the scientific data products produced by during the missions and so all the data that will be made available to the scientific community. Each data center is in charge to execute the scientific pipelines. Each of them can execute all the pipelines that are called processing functions, but each of them is responsible for the execution of some specific pipeline. And then as the responsible to store and deliver the product of the output data products. Each data center interacts with the EUCLID archive system in order to retrieve data needed by the processing, but also with other data centers. This is because the EUCLID archive system is responsible for data, metadata archiving and distributions. Is used by each data center to ask what data, where data are located with respect to the other data center, and to retrieve them in according to the needs of the pipelines that have to be run. In addition, the EUCLID archive system deals with the submission of the pipelines processing orders received to be sent to the science data center. So for this reason, to exchange the data, the different data centers interact with each other constantly. In particular, the SDC-IT-PROD that is hosted in Turin by Altec provides the 25% of the total amount of the resources in terms of computation and storage capabilities. In addition, it hosts the IoT tools for the instrument NISP that is mounted on the telescope. And this tool enables the end users to perform data analysis and produce instrument command requests that can be sent to the instrument when, for example, is needed a recalibration. The SDC-IT-PROD consists of 2 main infrastructures. The first one is the integration and test platform and is named SDC-IT-INT. The second one is the operational platform and is named SDC-IT-OPS. So the first one is the reference platform for the verification and validation process of the processing functions, but also for the software that are released by the EUCLID consortium. Instead, the OPS is the operational environment that is the target environment where the pipelines for the data processing are executed during the routine operation phase. For what concerns the infrastructure of our PROD platform, we have of course, it has been designed taking into account concepts like such as the scalability, the reliability, the maintainability, the usability, and security of the system. In particular, we have the components represented in this graph, but due to the lack of time, we will mention some details about only some of them, in particular the red ones. We start with the data processing subsystem. Of course, it aims at giving to the system the ability to execute the scientific processing functions. It is mainly composed by the HAL, that is the infrastructure abstraction layer, that is delivered by the EUCLID consortium and integrated in each data center. And it's a software that leverages the HPC cluster to execute the processing pipelines. In particular, we have 2 different modules, that is the YAL Metascheduler and the Pipeline Runner. The first one is in charge to pull the processing orders from the EUCLID archive system to prepare the working directory and then to retrieve the input data needed by the processing pipelines, asking them to the distributed storage system, and if not present in the internal DSS, the data are asked to the EUCLID archive system that can say where the data are physically located and enable the DSS of data science to retrieve data from another DSS. Then the metascheduler performed the scheduling of the requests to the pipeline runner, which splits the jobs into smaller tasks that are then submitted to a queue and then give to the HPC cluster that has the goal to the aim to run them until each job is considered successful. The HPC cluster is based on Slurm. In particular, Slurm is the workload manager that is in charge of organizing the cluster resources assignment. And for the time being, the Ops cluster is composed by 2 Slurm controller nodes, 12 Slurm processing nodes, and 1 Slurm database nodes. Of course, the int environment has a similar architecture, but with a less number of resources. The actual configuration provides a total number of about 1,500 virtual core, but they will be 6,000 by the end of the mission. Then we have the data exchange. That is the subsystem in charge to enable the exchange of the data products between the different data centers. It is mainly represented by the DSS, that is the distributed storage system, and it is a software that provides the ability to retrieve the data from the data persistence of the other data centers if in the data persistence in the internal data persistence the data are not already present. All the DS instances constantly exchange data over the HTTP protocol. Then we have the data persistence that, of course, is the part of the architecture that deals with the storage of the output data products in the local hierarchical storage. That is mainly composed by 2 tiers. The tier 1 is dedicated to the high performance archiving. The tier 2 is dedicated to the long-term archiving. In particular, we have that the tier 1 is support the real processing, and it is something, it is the only layer which the user source systems interacts. It is based on Lustre, that is a parallel file system that provides high performance in terms of I/O and a total capacity of 700 terabytes. Instead, the tier 2 is the long-term archive of the platform, so all the data that are no longer needed by the high-performance storage are moved to this one. Every time a data is moved to the tier 2, our reference remains on the tier 1 so that the users can constantly use also this data, and the data when needed are real-time moved from a tier to another. The transfer services is named data management framework, so is based on some data policies. For example, he can move data produced before a certain number of days fixed in configuration, and he can perform this task only when a certain threshold of the storage capability of tier 1 is overcome. Finally, we have the science support subsystem that aims at providing to the scientists the possibility to inspect the data. It is based on the Jupyter technology, but it can use both data from the int and ops platforms. In addition, the operators can submit HPC jobs to the int cluster in order to exploit the data produced by scientific pipelines. So we can conclude saying that the management of huge data amount such as the ones produced in missions like these represent a challenging task for the preparation and execution of the ground segment operation. So when designing a system of this kind, some crucial factors have to be taken in consideration. For example, the availability of an HPC processing infrastructure able to process mission data within specific time constraints, again, the performance of the network link between all the ground segment actors must be consistent in order to avoid latency issues. So I will thank you for your attention. And I'm here.
Thank you. Thank you, Chiara. Without having you noted that you're not part of the author team, one would not have noted this in your presentation. Okay. Can we take still a question? And maybe you can, is there a question? So thank you all for staying here in the session, and all the speakers for being on time and interesting discussions and presentations. Thank you.